We're going to talk about dynamic programming, which is a very important skill to have that could help reduce the time complexity of a lot of recursive functions. So first, let's talk about what dynamic programming is. It's a method of splitting a problem into smaller subproblems and solving the smaller problems. So this might sound a lot like recursion, but it's different and it's often a lot faster than it. There's two main styles, top-down and bottom-up. We'll see later that bottom-up is usually faster than top-down. So when should you use it? You should use it when the solutions to the subproblems are the optimal solutions to the main problem. So this is also known as a greedy algorithm. The subproblems also use solutions that rely on each other. So you can't divide and conquer, so something like merge sort wouldn't be classified as dynamic programming. Another way to think about this is that you remember the solutions that you already calculated, store it somewhere, and when you need to solve the main problem, you can use these already calculated solutions. And in addition, you can use it when recursive solutions time out. You can try to convert something from recursive to dynamic programming. So we're going to jump right into an example, which is the Fibonacci sequence. Hopefully you guys are all familiar with this sequence. This is the recursive implementation of it. And basically, the function fib takes in a number n, which is we're trying to calculate the nth Fibonacci number. If n is less than or equal to 2, you return 1, which is the base case. Otherwise, you go into the recursive step and return the sum of the two previous Fibonacci numbers. This is really easy to write, but the time complexity is O of 2 to the power of n, which is terrible. You never want exponential time. And something that you can notice is that when we need to calculate something like fib 10, we need to calculate fib of 9 and fib of 8. However, fib of 9 also needs fib of 8, but you calculate it twice. It would be nice if we can store that number somewhere and then just directly use it instead of calling another function to calculate it. So this is the top-down implementation. So this is going into the dynamic programming. It's really similar to before, but now we have a global vector of integers called memo, and we initialize it to all negative ones and to have a size of 1,000. So this is going to be the upper bound of what we can pass in. Otherwise, the function is really similar, except before returning, you set memo of n to be the number that you're going to return. This way, if we see that we've already calculated memo of n, we can directly return it instead of recursively trying to find it again. Some drawbacks of this implementation is that we need to know the upper bound of the input. So here we set it to be 1,000, and it's O of n time O of n space, because it depends on the maximum input, and there's still a lot of function calls. So for an n sufficiently large, it could crash your system. This is a bottom-up implementation that's a lot better. You initialize with a vector of integers memo with size 3 and initialize it all to -1, and then you set the element at index 1 and index 2 to be 1. These are the base cases, and then you loop from I equals 3 up until n, and you basically just add up the last two numbers in our vector and push it to the end. We've converted a recursive function to an iterative function, and this is now the same O of n time O of n space, but the thing is we don't need to know the maximum input. It'll just grow the vector automatically. But can we do better than this? And the answer is yes, we can do better. So from the last function, notice that all we need were two integers, the integer 1 before and the integer 2 before. We didn't need the entire vector. So here we've replaced that vector with just two integers, and we do the same thing iterating through inside the for loop. Instead of pushing back a number into the vector, we find the sum and then we shift everything back one. So 2 before is now equal to 1 before, and 1 before is equal to the sum of the two. This is O of n time, and now it's only O of 1 space. So now let's jump into Elite Code Hard, because those are the fun problems. This is number 72, edit distance. So if you want to tackle that before watching the next section of the video, feel free to pause here. Otherwise, we're going to jump straight into the problem. So the problem says, given two strings, word 1 and word 2, you want to return the minimum number of operations required to convert word 1 to word 2. You have the following three operations permitted on a word: either insert a character, delete a character, or replace a character. So the first time you read this, you might not think of dynamic programming immediately, but it actually has all the characteristics. the subproblems are basically word 1 and word 2 without either of their last characters. You can think of it as word 1 without their last character compared with word 2, or word 1 compared with word 2 without the last characters, or both of them not having the last character. So here's the intuition. The three cases of inserting, removing, and replacing can be simplified. If you insert a character into word 1, then the number of characters that are different will decrease by 1. And it's the same as removing a character from word 2. Another thing is removing a character is kind of like the opposite of that. It's the same as inserting into word 2. And replacing a character is like removing that character from both words. So here is the pseudocode for the function. You first have 2 pointers pointing to the beginning of each word. And then while neither hits the end of the word, you check if the characters at the 2 pointers are the same. If they're the same, then we don't need to do anything because the minimum number of operations won't change. Otherwise, we have 3 options, which is to remove the character from word 1, remove the character from word 2, or remove both of them. And since we're finding the minimum, we want to find the minimum of these 3 options. And finally, return the minimum. Some miscellaneous things before we get into the actual code. The base cases are when either of the words are blank, the minimum is the size of the other word. So let's say word 1 was blank. Then to get from word 1 to word 2, you would need to add all the letters of word 2. So the minimum number of operations is the size of word 2. Similarly, if word 2 were blank, it would be removing all the letters from word 1. And since we're dealing with 2 strings of different sizes, we need a 2-dimensional vector to keep track of all our minimums. So putting that all together, this is the solution. The function takes in 2 strings, word 1 and word 2. First, initialize R and C to be constants for the later loops. And then you initialize a 2-dimensional vector of dimensions R and C, filling it all with -1. The next 2 for loops are base cases. So these are the 2 base cases we just talked about. If either one of the words has size 0, then it's the minimum would be the size of the other word. The next for loop, so this nested double for loop, is our main dynamic programming part. So you first set memo of I sub j to be equal to the minimum of memo I minus 1, j, and memo I and j minus 1 plus 1. So these 2 are the cases are if you remove a letter from word 1 or remove a letter from word 2. And then the plus 1 at the end is because we're adding something that we did. And then we check if the characters at the 2 locations are equal. If they are equal, then we can also set memo of ij to be the minimum of memo of I minus 1, j minus 1. And this is because it won't change. So having the same character would be the same as not having either of the character. Otherwise, we can do replace. Replacing would be the same as memo of I minus 1, j minus 1, and then add 1 because that's another thing you have to do. And at the very end, you return a memo of the size of word 1, size of word 2. So thank you for listening. Hopefully this was very informative. Now you can go practice with your new knowledge of dynamic programming with even more LeetCode problems. Thanks for listening.